is to find the voltage. Okay, so we're gonna find V0 and then sketch the transfer characteristic. Okay, so now we have two diode, D1 and D2. So what I'm going to do, gonna distinguish cases. So case 1, before we do that, as we always do for our diode circuit, so let me draw the characteristic. So the IV characteristic of the diode. So the diode is on. Okay, so this voltage is a VD on. The diode is off in this region and is on when the threshold voltage, when the voltage across the diode is bigger than when the voltage supply is is more than the threshold voltage. Okay, so we are going to distinguish 4 cases. So diode, so 1, diode D1 is on and D2 is off. Okay, 2, D1 is off and D2 is on. 3, D1 is on and D2 is on. And 4, D1 off and D2 off. Okay, now let's look at the cases. So case 1, D1 on and D2 off. So in that case, ID1 must be positive for this diode to be on. So under what condition this is true? So I'm going to redraw the network here. So VI is there and have the resistor there. So D1 is on. That means we have VD on. So the assumption is that the diode are the equivalent. Okay, so let me write it here. D1 and D2 are equivalent. So then we have the bias voltage, which is a V, and we have the resistor. So the direction of the diode current will be this, ID1. Okay, so the diode is facing that way. So when I write KV here, the voltage here, so I have VI will be equal to negative R ID. I'm going against the current. When I apply Ohm's law, that's what I have, minus VD on. So minus V and minus R ID1. So I had -2R ID1 minus VD on minus V, which is VI. So 2R ID1 equal to minus VI minus VD on minus V. So ID1 must be positive. This implies that minus VI minus VD on minus V is positive. That means minus VD on minus V is bigger than VI. So in that case, what is the output voltage? So V out will be equal to negative VD on minus V, okay, minus R ID1. So it's minus VD on minus V minus R times ID1, so which is minus VI minus VD on minus V, right? So I take it from there, divided by 2R. So the R cancels out, so now I have negative VD on minus V plus VI over 2 plus VD on over 2 plus V over 2. Excuse me. So then that gives me VI over 2 minus half V and minus half VD on. That's V0. So if there's no algebra error, let me double check. That's correct. So V0 for case 1, V0 got VI over 2 minus half V minus half VD on. So when VI is less than minus V minus VD on. Okay, so if this was ideal diode, then VD1 will be 0. Okay, so that's case 1. Now case 2. For case 2, what do we have? Have D1 off now, D1 off, and D2 on. So D2 on mean ID2 must be positive. So in that case, I'm gonna draw the network. So we have VI and I have the resistor R. Now D2 is on. So when I copy this down there, you see I have it in front of me. So I can paste it here. Okay, paste it here. So in that case, what do we have? We have D2, so VD on, and I have V, then I have R, and that's the second branch there. So I'm taking this branch now, right, that's this, and the voltage is still V0 there. So the current to the network will be ID2 based off the orientation of the diode D2. So I can write my KVL, so I know that VI will be equal to RI D2 plus VD on plus V plus RID2. So that give me 2 ID2 plus VD on plus V. So I 2 RID2 is VI minus VD on minus V. So because ID2 must be positive, that implies that VI minus VD on minus V must be positive. So VI must be bigger than VD on plus V, and the output V0, which is VD on plus V plus RID2. So that's VD on plus V plus R times VI minus VD on minus V divided by 2R. Okay, so that comes from here. So that gives me VD on plus V plus half VI and minus VD on over 2 minus V over 2. So it gives me half VI plus half V plus half VD on, that's V0. So for case 2, we have V0 equal to 1/2 VI plus 1/2 V plus 1/2 VD on. So if you're dealing with ideal diode, VD1 will be equal to 0. Then you end up with half VI plus half V. So the condition is that VI is bigger than VD on plus V. Now, case 3. So for case 3, what do we have? We have D1 on and D2 on. So D1 on and D2 on. So I'm gonna paste the network here. Okay, so for this case, I'm gonna redraw the network. So V I and resistor R, the diode D1, so VD on, and have V, have the resistor R, and we have VD on. I have V and the resistor R. So what I'm going to do, I'm going to write KVL. So first of all, the current ID1 is there and ID2 is there, so they're both positive. So the assumption is that ID1 is positive, ID2 will be positive because they're on. So what I'm going to do, I'm going to write KVL around this loop. So that gives me RID1 plus V plus VD on plus VD on plus V plus RID2 equal to 0. So we have RID1 plus ID2 plus 2V plus 2VD on equal to 0. But so V is positive, VD1 is positive. So, and the assumption is that ID1 plus ID2 terms must be positive. So the sum cannot be equal to 0. Okay, so alright, so if we want this to be positive, then negative 2V, negative 2. So well, when I calculate ID1 plus ID2 is equal to minus 2V minus 2VD on over R. So we want that to be positive, which is impossible because V is positive and VD on is also positive. So that means both diodes cannot be on at the same time. Under these conditions, both diodes cannot be on at the same time. And the condition that V is positive and VD on is also positive. So in that case, we don't have that case, right? So the last one So case 4. So case 4 is when they're both off. D1 is off and D2 is off. So in that case, we have this will be open, and this will be open. So I mean, there's no current in the network, so VI, which is equal to RI, right, times 0, there's no current, times 0, plus V0. So for this case, VI equal to V0, or V0 equal to VI. So let's recap. So we have V0 will be equal to, so the first one, so case 1, this is what we have. So I'm going to copy that down there. So that's what we had, and this is V0. Okay, so V0 equal to that. And case 2 is this. Now case 2 is this. Okay, and so when we're in between the two, so then when V0 equal to VI, so when minus when VI is bigger than VD on, plus V. So the other condition, so for this condition, then we have negative V minus VD on less than VI, VI less than VD on plus V, right? So, well, if you look at it, we have minus VD on minus V here. So, and then V plus VD1. So this cover this, this cover this. So what we have left is this, right, which is this. Okay, so we can sketch the output voltage on top of the input voltage. So if the voltage looks like this, the input voltage VI, so that's the V max. So minus V max. So this will be V plus VD on. So let me just remove this, make space. So V minus VD on. In between the two, the voltage are the same. So this and this. But then when it's bigger than VD on, then it's heavy, so it's gonna look like this, and it'll look like that. So that will be V out. Now let's sketch the transfer characteristic. So the transfer characteristic will be given by this. So we put our output voltage there, the input voltage here. Now so we have V plus VD on minus V minus VD on. Now, so between the two, the slope is 1. So this so for this one, the slope is like mx plus b, so v0 equal to vi. So between negative v negative vd on, less than vi less than v plus vd on. So that will give me this straight line to the origin. Now, so when it reach V plus VD on, then has a slope of half. Okay, so when we have this half plus also have VI plus half V plus half VD on. So it's mx plus b, so m equal to half. So the graph will look something like this. So the slope here is half, and here the slope is also half. So it looks something like this. So that will be the transfer characteristic.